Do you have any questions about previous lectures or about the problems? Uh, if no, then let's continue the previous topic. Uh, so we were studying two-dimensional Laplace or Poisson equation. So it is this equation Laplacian of u equals to rho, or this rho can also be zero. And it also has some boundary conditions. Maybe let me write it like this. Boundary and asymptotic conditions. So actually, if you want to study the true electrostatics, then this sign on the right hand side, and probably this factor should be different because conventions in physics are the following. So this first equation is a Laplacian u. Well, let me write it like this. There is an electric field equal to minus gradient of the potential. And one of Maxwell's equations tells that divergence of this electric field equals to 4 pi rho. Again, up to some constants. So in this convention, we have u equals minus Laplacian of u equals to minus 4 pi rho. But we will not care about this conventions. We will simply use this formula in this equation. Yeah, and what do we also know about this equation? We know how to solve it in R2 without any boundary conditions. So we know that its green function is 1 over 2 pi logarithm of absolute value of z minus z0 complex numbers. Maybe we can also write it as absolute value of vector r minus r0. So this Laplacian equals to delta function, dimensional delta function of r minus r0. And so we can say that green function is 1 over 2 pi logarithm of absolute value of r minus r0. Or in using complex numbers, it can be written as 1 over 2 pi logarithm of z minus z0. And the same. And we also know that this equation can be equivalently written in complex coordinates. So it is the same as to write d for d bar u equals to rho, when d and d bar are derivatives in z and in z bar. So it's an equivalent form. And in particular, we know that since it can be written in this form, we can either perform, either guess its solutions, or say that we can perform a separation of variables in radial coordinates and find them. But the point is that solutions of this equation in the appropriate domain, like on the plane without zero and infinity, have a form of Zn, so this Laplace Hamiltonian Zn equals to 0 when Z is different from 0 and infinity, and also d bar of Z bar n equal to 0, because one of these two derivatives kills either Z or Z bar. We know such solutions, and the knowledge of this solution plus knowledge about the Fourier transform allows us to solve some problems, some boundary problems inside or outside the unit circle. So we studied one simple example of this phenomenon with the homogeneous electric field. But now let us study a modern advanced version of that problem. So, namely, let us study a problem about a metal circle or cylinder, maybe better to say. Well, it depends on whether we look at this problem as at the 2D problem or the 3D problem, plus point charge. So this problem looks like this. We have a circle of radius 1, and we say that U on the circle is constant. We also have some charge at point 0 outside of this circle. And we say the charge of this circle is 0, which means the asymptotics of solution at infinity is defined by this charge only. Let us say that this charge is Q. So, so our problem mathematically looks like this. We have an equation Laplacian of U equals to Q times delta function of two-dimensional delta function of Z minus Z0. we have a condition that u of 1 phi, well, let me write it as r phi, r and phi are polar coordinates, and a complex coordinate is written like this. So u of 1 phi equals to constant. And this condition that the charge of this circle is zero tells us that the asymptotics at the infinity should be given by this charge only. So when r goes to infinity, u of r phi should behave like q over 2 pi log of r. So is a problem clear? So let us try to solve it in some naive way. Mm, so, suppose that we don't have this circle. So, and let us write the first approximation for solution of this problem. So how can we write a solution to this equation if we don't have any boundary conditions, if it is just an empty space? What, what will be the formula for u of z bar? Yes. So q over 2 pi logarithm of z minus z0. So and if we want to do something about this unit circle, we can first look at the boundary value of this function. We can see what happens when we restrict this function to this unit circle, because if you do this, we can then try to add another solution to this equation that does not have any charges outside the unit circle, but which has this precise boundary condition, which can cancel their own boundary conditions into our problem. So let me call this u1, and we can also say that it is a function of r and phi. It is of course equivalent parameterization. Yeah. So let us look at the values of this function at the unit circle. So Oh, we need to specify to z equal so absolute value of z equals to 1. So in this region, z is less than 0. And we can expand this logarithm as a series. So we can write that u1 is q over 4 pi logarithm of z minus z 0 plus logarithm of z bar minus z 0 bar. Maybe better to write like this: 0 minus z, 0 bar minus z bar. So we have a logarithm of something less than 1. So we have this kind of expression, right? And since we live at the unit circle, this expression, so we can say that z to the n is e to I n phi, yeah, just e to I n phi. Sorry, it is minus n. When absolute value of z equals to 1. So now the question to you. Can we add some other expression to this series such that it decays at infinity, but cancels this phi dependent boundary values? So we want to solve another problem that would cancel this series. Mm. So uh, and so we want this condition that it should go to infinity, in the sense that u1 and u2 have the same asymptotic conditions, and solve the same equation. But this new solution corrected by u delta should have correct boundary conditions. So we need to ask that this correction of u delta of mm, 1 phi is minus u1 of 1 phi plus in principle some constant. It doesn't matter. So, and this boundary condition is written here. We have just computed it. So this this series is u1 of 1 phi. So, so using this knowledge, can you try to write such a solution of a Laplace equation outside the unit circle? So it should decay at infinities, so it should contain negative powers of z. And its restriction to a unit circle should be this. So phi dependence on the unit circle is written here. Everything else are just constants. So. But which powers of R? So what should I write here? So u1 of u delta, this correct in term of R phi. What should it be? In principle, it should have. So this one has all Fourier modes. All coefficients in front of e to I and phi are non-trivials. So we should also have them here. So we should have I and phi uh, multiplied by something, but by what expression? So that they cancel. Um, Uh, yes, it's true, but at the moment I'm asking about this particular term because uh, so we have two sets of exponentials. The first set contains exponentials to positive with a positive coefficient. The second term contains exponentials with negative coefficients. And I'm asking about the prefactor for this exponential. What should what should its radial dependence be? So, so that it decays at infinity. Hmm? E? Oh, oh, what is this expression in polar coordinates? And they are killed by a Laplace operator. We could check it in several different ways. So, but what should we write here? Hmm? Yes. Thanks. And what else? Yes. Thanks. And what do we have in the next term? No, it should decay at infinity. Oh. Again, R2 minus n. Yeah. And that coefficient, the same as before, over n. Uh, but and now notice the following. The series can be written in terms of z and z bar, as before. So this is z bar to minus n. And of course, I missed the overall prefactor. So there was q over 4 pi here. Sorry. And also here. And now, can you sum this series? But what do you mean? No, it's true that it is a real expression, but what does it equal to? Hmm. Oh, so can you say it again? Logarithm of what? Mm-hmm. Ah. Mm-hmm. Mm-hmm. Yes. Thanks. Uh, mm-hmm. Yes. Thanks. And overall prefactor q over 4 pi. So this can be written as uh, so if you want to write it as a logarithm of differences, uh, then we can write it as q over 4 pi q over 2 pi maybe. Absolute value of uh, z minus 1 over z 0 bar. But there is also the overall minus sign here, right? So it is, this logarithm was a minus sign, a plus a logarithm of absolute value of z. So you see that this compensating solution that cancels the boundary condition it can be written as a combination field from two charges. One at 0, another at this inverse point. So if you combine all this together, then a solution to our problem is given by this formula. Mm. Q over 2 pi. So this is a true charge. So the picture looks like this. If you put this metal cylinder or circle in the field of some external charge equal uh, q, at a distance, so the radius of this circle is 1. So this is 1. When you put it into field of this external charge, it can equivalently be described as a combination of two charges. One at 0, and it equals to minus q. Another equals to q, and it is located in this point at the distance 1 over r. 1 over r, if this distance was r. So we see that this method of images works not only in trivial cases like reflection with respect to the plane, but also in such situations. So yeah, and if we want to, if we want to guess this result without a mode expansion, we can simply notice that equipotential surfaces in the system of two charges of opposite values located at 2 points are all circles. So So if we want to find the equipotential surface, then we want to say that logarithm of z minus z1 over z minus z2 absolute value q over pi equals to some constant c. Then if logarithm of this absolute value is constant, then this absolute value is constant as well. So we can write that absolute value of z minus z1 squared is some constant. And we can now write this absolute value squared as the product of this complex number times its conjugate. So z minus z1 times z bar and z1 bar is c tilde z minus z2 z bar minus z2 bar. So, and if we open brackets in this expression, we see that this equation transforms into 1 minus c times z bar plus some coefficient times z plus some coefficient times z bar plus some constant term equals to 0. And what is the curve in the complex plane that is described by this equation? For example, what happens if you try to rewrite it in x and y variables? So z is x plus iy. Yes, yes. So it can be written as 1 over c times x squared plus. So it's a circle with the center located somewhere. So this picture looks like this. There are two charges, plus and minus. And there is one equipotential surface right in between these charges. There are circles close to them, and there are some other circles located like this. So, and if you want to study such a problem, you can say that, well, if you want a constant potential on some surface, then we can simply take one of this exponential surfaces. And then if we don't like this potential or don't like the asymptotics, we can add another charge that keeps this surface equipotential but changes the asymptotics. So yeah, it was that simple. Are there any questions about this problem? So now let us try to study almost the same problem, but actually slightly simpler. So we want to find the gain function of this Poisson equation in the unit disk. So now it is inside. So we have this Laplace equation, Laplace NQ equals to 0 for absolute value of z less or equal than 1. Oh, sorry, not 0, but a delta function of z minus z0. And we have boundary conditions that u of 1 phi equals to 0. So, do you have any idea how we could solve this equation? Looking at this previous formula, it should be quite similar, and the idea is almost the same. So, we should definitely have something that gives a non-trivial delta function on the right hand side. So there should be some logarithm so we definitely have this. Can we cancel this somehow on the unit circle? Yes. What do you mean? Do you mean that we can expand this logarithm? Uh, uh, yes, yes, it's true, but is there any other way to guess this formula? Like, of course, it is doable, but if you already know about this reflection trick, can we adjust another term that cancel this one on the unit circle? So I can propose to rewrite this expression like this. So this dots should be guessed, but this first equation can be written like this: 1 over pi logarithm of absolute value of z times absolute value of 1 minus z0 z inverse plus dots. So I can rewrite it in this simple way. It's equivalent. But also notice that if we live on the unit circle, uh, then z inverse isn't the same as z bar. There is this remark. And if you use this remark and look at this expression, can we guess that second term that is analytic inside the unit circle, but canceling the asymptotics of the first term? No, not argument, but we can replace the inverse by z bar. Because this term will be analytic inside the unit circle, because the 0 times the bar are less than 1, it will not have singularities, but they coincide on the unit circle. Right? So, so So if we put, so this is analytic when z is less than 1. Mm, So, because absolute value of z 0 times z is less than 1. Z 0 is also inside the unit circle. Mm, uh, and it coincides with this logarithm if absolute value of z is 1. So is it fine? So we could guess on the solution, and well, and of course it has almost the same form as before. It have this mirror charge with opposite sign. So altogether, this equals to 1 over pi over 2 pi logarithm of z minus z0 uh, uh, 1 minus z bar times z0. So this is the green function with these boundary conditions. Let me check. So, do you have any questions about it? Okay, let's go further. So we can notice the following thing, that we were solving this problem for a gain function with delta function at point z0, and we obtained this formula. G of z0 is 1 over 2 pi logarithm of z minus z0, 1 minus z bar times z0. But if we exchange these variables, it will be the same, because absolute value of a complex number or of its conjugate is the same, and the absolute value of -1 is 1. So we can notice that g of z0 equals to g of z0 z. So is it clear that it has such a symmetry? And now let's understand the origin of this symmetry. So it looks like a symmetric matrix. In the sense that A of G of ij equals to G of ji. So and we know that this gain function was the inverse matrix in some sense to the Laplace operator. So well, the question is why is it true? So our gain function is the inverse operator to the Laplace operator. And to prove that it is symmetric, we need to prove that Laplace operator is in some sense symmetric. What is the definition of symmetric operator or symmetric matrix in the finite dimensional space? So to define this, we need to have some scalar product, because if we don't have this, then our operator has a kind of one upper index and one lower index, because it acts from the space to itself, and there is no way to exchange these indices. To be able to define something symmetric, we need to be able to pair the elements of space where it acts. So we should define a scalar product in the obvious way. So Scalar product of two functions on our domain D can be given simply by this integral. Oh, actually, it works on the arbitrary dimension. And so we can restrict to real functions, mm, but it doesn't matter. In our case, everything is real. But in general, we can write this one-half linear form. F bar of x times g of x. So it's a positive definite scalar product, non-degenerate, since it vanishes only if the square of function vanishes only when a function in itself is 0. We can define this, and now let's prove that Laplacian is symmetric. Symmetric or self-adjoint, depending on how we define the scalar product. Or maybe better to call it symmetric in all cases. Yeah. So if we want to define some symmetric or Hermitian matrix, then what happens if you try to move it to the first place in the scalar product? So what is it by definition? This is a Hermitian product. I don't know how to call this. Let us call it Hermitian. Let us, don't know, put here letter C, although it's not a conventional annotation. And we can also define a real scalar product for real functions.
So we are considering complex value function in general.
Yes, because
by symmetric we intend to be self-adjoint.
Self-adjoint is a more general term which uses something from functional analysis. But to be on the safe side, we can say that it is either symmetric in one case or a Hermitian. So if we consider this real scalar product, then we can move this operator to the first place, adding sign t, which means transposition, by definition. And if it was a Hermitian scalar product, then it will become Hermitian conjugate. By definition. So is it fine? So we can check this definition in the finite dimensional case. So scalar product of u and v. Real scalar product is sum of ui vi. Hermitian scalar product is sum from 1 to n u I bar vi. So suppose that we have an operator delta that acts on v, and its ith component equals to sum over j delta ij v j. Then u with delta v is a sum from one from 1 to n ui delta ij v j. Which can be written as a sum and here sum from j. Which can be written as a sum from, we can write it, we can exchange I and j indices of summation, so that the outer sum is now over I. So we exchange I and j and exchange the sums. Or maybe let's better to simply exchange the sums. Like this. So we see that delta is summed with u by the first index. So we can write this as and in the original formula, this summation was over the second index, like in the usual matrix product. So we can say that it equals to sum from j equals to 1 to n, sum from I equals to 1 to n u. So let me write it like delta transposed ji with j. So it's a scalar product between delta transposed U times B, where matrix elements of delta transposed Ji equal to delta Ij. So, and in the same way, we can compute same quantity for this Hermitian scalar product, but here we would need to add a complex conjugation. So, delta Hermitian conjugate Ij will be delta Ji complex conjugate. So it's a justification why I transpose the operator to the grain function will be grain function with exchanged arguments. So absolutely in the same way, you can change this finite summation to integration, and then well, maybe it doesn't follow, but it can be obtained by exactly the same computation that G transposed of Z1, Z2 is the same as G of Z2, Z1. And then the same for Hermitian conjugate. So is it fine? Okay, so we understood that this transposition does this, and we need to check why a Laplace operator is symmetric. Or if it is not naively symmetric, then what do we need to do to make it symmetric? So we need to prove this. And it's a simple but important computation that will appear later, because the fact that it is symmetric and it is actually self-adjoint will help us to build a general theory for this analog of Fourier transform or other mode expansions. So we need to check that Laplacian transposed is the same as Laplacian. So let's consider this a scalar product, f with Laplacian of g. This equals to integral over our domain D, dn x, f of x, divergence of gradient gradient g. So this can be written as integral 1 over dnx. So I'm basically integrating by parts in this multi-dimensional case. And we have actually seen such kind of computation when we studied energy functional. So we have this, and we need to integrate it by parts once again to move the operator to f. So we write it as do you agree with such an expression? So, so in this step, if you compute a gradient of this divergence of this expression, we will have this scalar product when we differentiate f, and it cancels. And the second term will be divergence of a gradient, which gives Laplacian of g. And at this step, we in this step, this product of gradients survives, and the Laplacian of f cancels. So we can just think about this a bit more carefully, but actually we can think that this computation is performed in each variable independently, because this Laplacian is a sum of derivatives in each coordinate. So one-dimensional and n-dimensional problems are absolutely the same. Yes, so now we have this integral over the domain D, which has precisely the form we need, plus these two terms that can be computed as a surface integral. So we can write it is a Laplacian f times g plus the integral boundary of d dn f gradient g minus g gradient f. So and uh, if we live in the space of functions that satisfy directly our Neumann boundary conditions, then one of these two terms should necessarily cancel. And one more remark is that we can also apply mixed boundary conditions in the sense that this normal derivative of g should be proportional to g itself. And in this case, this also vanishes, but not for each term separately, but this combination will vanish. So, so continuing this equality, you see that if we impose appropriate boundary conditions on f and g, then this operator is symmetric, plus f times g. And of course, all this would work if we use the complex scalar product, because Laplacian commutes with complex conjugation. So, do you have any questions about on this? Yeah. Okay, so now we have this condition, and we can prove the symmetry of the gain function. So we have something like this, that f a scalar product with a Laplacian g equals to, let's start from f g equals to this, then it equals to Laplacian transposed g G. Then it equals to G transposed, Laplacian transposed, which is equal to Laplacian itself. We can move them more or less by definition. So we obtain immediately that if Laplacian action G equals to 1, then G transposed and the Laplacian equals to 1 as well. And now we can act with this construction on the original gain function. So this is 1. So G transposed equals to G. So it's expected for the symmetric matrix. The only tricky thing about this formal computation is that you can remember the gain function for the wave equation, which was not symmetric. It was vanishing when t was greater than no, t was less than t prime, but it comes from the fact that solution of this equation for the gain function is not unique. So, and it doesn't make sense to think about it in such terms. Not for Laplace operator, it's not the case because it usually does not have kernel. So, do you have any questions about this? Yeah, and let us discuss one more question, which we briefly discussed for the wave equation. And this is a question about relation between different gain functions. So I haven't raised this formula yet, and therefore we can try to use it because it's a useful technical computation. So let us suppose that we know how to solve the problem with zero boundary conditions. Well, we know this gain function that solves solves the Poisson equation with delta function on the right hand side. or maybe let me write it like r 0 delta of r minus r0, and g of r0 restricted on the boundary of our domain is 0. So we know this eigenfunction, and but we want to solve a problem with non-trivial boundary conditions. So now we are right inside, but with non-trivial boundary conditions. So u of r should either be u0 of r or n derivative with respect to normal direction of u of r. It can be u1 of r. They're clear or Neumann boundary conditions. So let us try to substitute this function g and this function u into our formula. So suppose that we already know them. So we know one of them for sure, but suppose that we also know u. And let us substitute into this formula. So we know the integral over d. So let us substitute u Laplacian g minus g Laplacian u in the integral over so do you agree that we have such a relation? So this is what is right on this blackboard. I simply combine it in a slightly different way. Yeah. So because this was equal to integral over d for divergence of u gradient g minus g gradient u. So you can check that these two expressions coincide, and this was obtained by Stokes' theorem. Mm. But now, can you tell me what this two terms equal to? Hmm? Do some of this. Can we actually compute this integral? Yes. Hmm. Yes. Yes. So this term is 0, and this gives a delta function, so it's integral over d u of u of so I was using x r. Let me write r here as well. U of r delta of r minus r0 dnr. So this is yes, it's simply u of r0, and this is what we want precisely, because because this integral is already restricted to the boundary, and on this boundary we have fixed boundary conditions. So, uh, uh, well, actually, this works only in one of those cases, because we want one of these two integrals be equal to 0. So let us see when this works. Mm. So if gradient of u, if gradient of g times n is 0, uh, then it equals to uh, minus integral g gradient u. Which is E1 in this case. So if we want to solve the boundary problem with Neumann boundary conditions, we need to take the gain function for the same problem with zero Neumann boundary conditions, and simply restrict one of its variables to the boundary. And so this gain function is expressed in the gain function is simply equal to the gain function with one specified variable. If this gain function was for Neumann, for a Dirichlet problem, like in our case on the boundary, so if maybe let's try it like this. Oh, this gain function vanishes on the boundary, so it's gain function for the Neumann for the directly boundary problem. Then this term disappears and this one survives. So this integral equals to integral of dn gradient g times u, which is integral dn gradient g times u0. It's this directly boundary condition. So comparing this, we know that u of r0 is equal to integral over dn gradient of g times u0, integral over the boundary 0 of r. And gain function is of r r0. Right? And let us try to apply this knowledge in a very simple problem. Hmm?
Why the G is not in the direction of 0?
No, there are two options. One is Neumann, another Dirichlet.
We are putting Neumann on both G and U.
Yes.
Okay.
Maybe it was better to write that we should study both gain functions here as well. So it's another alternative. If we want to solve a Dirichlet boundary problem, we need to have a corresponding gain function for zero boundary conditions. So can you tell me the gain function in this case? There is 0. What is g of z and z0? So it can be solved. Yeah, the Dirichlet boundary conditions are 0 in the sense we are solving this equation. Of S n of u equals to delta z minus z0, and u respecting on r is 0.
We do the same what before,
Uh,
and we start on the whole R2
uh,
and then search for correction.
yes, but what kind of correction should it be? Can you just guess it immediately? Gain function is proportional to charge and to logarithm of distance to this point, and we want to solve this equation only for imaginary part of z is greater or equal than 0. We want to solve it in the upper half plane, so in principle we can add arbitrary images in the lower half plane. So what can we add there so that it cancels our gain function on this real line? There was actually a picture of this equipotential surfaces between two charges. Which looked like this. So this was plus charge. And, oh, what should we do?
So maybe the correction is like adding the logarithm centered in minuses the
Well, it's not minus because minus. So if you draw coordinate axis and then minus z0 is here, but we need conjugate. Oh, sorry. Oh yes, it should be minus a charge at point z0 bar. So the gain function of z0 will be 1 over 2 pi logarithm of z minus z0 over z minus z0 bar. Yeah, but uh, we don't have time today, so we'll probably finish this computation next time. But you can also do this at home and check that if you first compute this gain function and then send the point z to the real line, that that this expression turns into the delta function as it should be. Because if you are looking for solution to a boundary problem, it should reproduce in boundary value when we are approaching the boundary. So, but in any case, we'll do this computation tomorrow, and we'll see this delta-like sequence. So, okay, thanks for your attention.